AS Paper 2, June 2016. Let's have a look at question 1. So we've got some ethene and some steam in a reversible reaction making some ethanol. Write an expression for the equilibrium Kc for this equilibrium to deduce the units of Kc. So it's the concentration of ethanol divided by the concentration of ethene and also divided by the concentration of water. Nothing's squared, so it's just the straight concentrations because we've got the number 1, 1 and 1 in front of each of these quantities. In terms of units then, we've got concentration on the top and 2 concentrations on the bottom. So we've got moles per decimeter cubed on the top and moles per decimeter cubed and moles per decimeter cubed on the bottom. So the 1 on the top will cancel with 1 on the bottom, so we'll end up with moles divided by decimeter cubed on the bottom. Moles per decimeter cubed on the bottom, so moles divided by decimeter cubed on the bottom, or moles dm to the minus 3 on the bottom, and then when you take that to the top, that becomes, instead of moles dm to the minus 3, it becomes moles minus 1 dm3. The equilibrium mixture is found to contain numbers of moles of ethene, moles of steam and moles of ethanol, and you're given a volume. Why would you be given moles and a volume of a container that they're all in? The only reason is to work out concentration. Concentration is moles divided by volume. So the concentration of ethene is 0.7 divided by 2. It's already in decimeter cubes, that's fine. Concentration of steam is 1.20 divided by 2. And concentration of ethanol is 4.4 divided by 2. You put those numbers into this equation. 4.4 divided by 2 divided by, for the ethene, is 0.7 divided by 2, and then for the steam, the water, is 1.2 divided by 2, and it comes out as 10.5. To 3 significant figures, 1.2 zeros, 3 significant figures, 4.4, 2.00. So some of these values are to 3 significant figures. This one's to 3 significant figures as well. They're all to 3 significant figures, so 10.5 is correct. Question 2. So I'm heating up some water using methanol in a spirit burner. I've got the mass of the burner before and afterwards, so I can work out the mass of methanol. But to start off with, I'm going to concentrate on the beaker and the amount of water and the temperature rise. And I'm going to use Q equals MC delta T. The mass of the water I've probably got, yes, 100 grams. MC, the specific heat capacity, I've been given 4.18, so I must be using Q equals MC delta T. And the temperature changes are worked out for me as well, 38 degrees C. So my first thing that I've got to work out is Q equals MC delta T. 100 multiplied by 4.18 times 38 is 15,884. I can put a minus in front of it, so because it's exothermic, so minus 1,584 joules of energy are given out. I could convert that into kilojoules. Joules going into a larger unit value of kilojoules, you divide by 1,000, so that would be 15.884. I think I'll leave it as joules just for now though, because I know that the moles of methanol I've worked out the mass of methanol. So the mass of methanol by taking 214.02, taking away 212.37, I've worked out that I've got 1.65 grams of methanol burnt. I know that methanol is CH3OH, that's a 14, add 3 ones, add a 16, add a 1, so it's got a relative formula mass of 32, and moles is mass divided by relative formula mass. I've got 0.0516 moles of methanol. So 0.0516 moles of methanol gives out 15,884 joules of energy. Now I've got to work out what would be given out if it were a kilojoule per mole. Well, this amount is very much less than a mole, gives out 15,884, so if I divide 15,884 by this small amount, it will tell me the number of joules of energy that would be given out if I had a full mole. So heat change per mole, I divide by 0.0516, and it turns out to be 308,000 joules for a mole of methanol burned. I can now divide that by 1,000, and it tells me it's 308 kilojoules now rather than joules, per mole of methanol burnt. It's a minus number, so it's minus because the enthalpy change, then the enthalpy of combustion is minus because it's an exothermic reaction. Suggest a reason other than incomplete combustion or heat transfer why the students value. Well, there's three reasons really why you might get values different from the data book. The main one is heat loss, heat transfer to the atmosphere, heat loss. We can't use that one. The next one is that the fuel doesn't burn completely, incomplete combustion. And the third one is that the actual beaker itself, the copper container, actually absorbs some of the heat. So heating up the copper container will be another source of error. The uncertainty. The temperature readings from the thermometer in this experiment was plus or minus 0.025. That means that the thermometer can be 0.025 out. This gave an overall uncertainty temperature of 0.05. That's because you're taking two temperature readings. So you're taking a temperature reading at the beginning and at the end to work out the temperature change, and that's why they've doubled the error, because you could get an error the first time and an error the second time, and so those errors are cumulative, added together. So I've got an uncertainty of 0.5. Calculate the percentage uncertainty for the use of the thermometer in this experiment. So I now need to take, say I could be 0.5 degrees C out of my temperature change. My temperature change is 38. So I could be 0.5 divided by 38 multiplied by 100% gives 1.3. I'm taking it to, these numbers here are to, this one's to one significant figure, this one's to two significant figures, so I'll take it to two significant figures. The 17 is to two, the 38 rather is to two significant figures as well. So 1.3 is a reasonable sort of level of accuracy. The student said correctly that using a thermometer and an overall uncertainty of the rise of temperature of 0.5 was adequate for this experiment. So the thermometer has got an error on it, but the student said it was adequate for the experiment. Explain why it's adequate for the experiment. So even though the thermometer's got an error, there's probably a bigger error somewhere else, and the main errors are these three: incomplete combustion, heat transfer to the surroundings, or heating up the copper container. The main one is heat loss to the surroundings. So heat loss to the surroundings, heat transfer to the atmosphere, is your biggest error. So really this is insignificant in comparison to heat loss. The enthalpy of combustion of ethanol is minus 1371 kilojoules per mole. The density of ethanol is 0.789 grams per centimetre cube. Calculate the heat energy released in kilojoules when 0.500 decimetre cubed of ethanol is burnt. So why would they give you a density? Density is mass divided by volume. They've given you a volume, so they've given you density and they've given you volume. Density is mass divided by volume, and they've given you the density, they've given you the volume. They must want you to work out the mass of ethanol. That's the only way that the only way that we could go if we've got density and volume. So what we've got to do is density is mass divided by volume, so mass is density multiplied by volume. The mass of the ethanol is 0.789. Now it needs to be, look, the density is in centimetre cubed, so we need to turn decimetre cubed into centimetre cubed. A larger unit going down to a smaller unit, like decimetre cubed going down to centimetre cubed, you multiply by 1,000. So 0.5 multiplied by 1,000 is 500. So density multiplied by 500 centimetre cubed is 394.5 grams. That's the mass of ethanol. Now I can always work out the MR of ethanol. So ethanol is CH3CH2OH. So when I work out the MR, it works out as 46. 2 carbons are 2 12s each. The hydrogens, So there's 6 hydrogens in there, a 6 and a 16 for the oxygen, 46 for ethanol, and so I can work out the number of moles. 394 divided by 46, 8.576 moles of ethanol. Well, minus 1371 kilojoules are given out when I burn per mole when I burn 1 mole. So the question's saying how much energy would be given out if I burn 8.576. So it's minus 1371 kilojoules for 1 mole multiplied by 8.576, and it comes out as 11800 kilojoules of energy released. 3 significant figures, must be at least 3 significant figures, so I've got at least 3 significant figures here to match the 3 significant figures in my answer, in my question. Question 3. Isooctane is added to petrol to increase its octane rating. Some high-performance engines require fuel with a higher octane rating. Write an equation for the complete combustion of isooctane. Use the molecular formula C8H18 of isooctane in your equation. So it's C8H18 plus O2. If it's complete combustion, it's going to make CO2. Incomplete combustion, of course, would make carbon monoxide, CO, or possibly carbon. And it always makes water. So I've got C18, H18 makes CO2 and water for complete combustion where there's a plentiful supply of oxygen. To balance this, then the C's end up in the CO2s, so 8 C's must end up with 8 CO2s. The 18 H's, well, the only place where the H's can go are into the water, H2O, 9 2's are 18, and then you add this up, 8 2's are 16, add 9 is 25, so what number multiplied by 2 equals 25? 12.5, 12.5. Explain in general terms how a catalyst works. Well, it provides an alternative route and lowers the activation energy. An alternative route for the reaction to lower the activation energy. Carbon monoxide is produced when incomplete combustion takes place in the engines. Nitrogen monoxide, that must be NO, like carbon monoxide is CO, is another pollutant. How can they react together? So you've got CO plus NO, and they make carbon dioxide and N2. So carbon dioxide is released into the atmosphere, it's a greenhouse gas, and nitrogen is a gas that's about 78-79% of the air is nitrogen anyway. Platinum, palladium, rhodium are metals used inside catalytic converters. These are very expensive. Platinum is used to make some of the most expensive jewellery in the world. A very thin layer of these metals is used on a honeycomb ceramic support. So there's some kind of ceramic honeycomb middle, and then the metals, the expensive metals, are used as catalysts on the outside. Explain why a thin layer is used this way. Well, it exposes the gases to the thin layer. You can also save money by using a thin layer, and the thin layer of metals mean then there's a greater surface area to come into contact with the gases. So less metal is needed, so you're going to save money. Increase it, although less metal is more important really than saving money, although you do save money. Increase surface area on the metal because it's on the surface, and a greater proportion of metal is therefore on the surface. What's happening here? Oleic acid looks like this. It's got a double bond, it's got a carboxylic acid. Identify the reagent that could be used in a chemical test to show that oleic acid is unsaturated. Unsaturated means it's got a double bond, and indeed it has here. So even though it's got a carboxylic acid group, the common mistake will be to say add sodium carbonate and look for bubbles. It's not actually asking that, it's asking for unsaturation, so it's asking you for test for this double bond here. So your answer is bromine, or bromine water, goes from orange to colourless. So question 4. Explain why the relative molecular mass of propanal and prop-2-ene-1-ol by mass spectrometry could not be used to distinguish between these samples of these two compounds. So if you actually look at propanal up here, then it's got 3 carbons, 6 hydrogens and an oxygen, and so is prop-2-ene-1-ol, 3 carbons, 6 hydrogens and 1 oxygen. So your answer is that they contain the same number of each type of atoms, 3 carbons, 6 hydrogens and 1 oxygen, or you could say that they've got the same molecular formula. So use the spectrum to identify which of the compounds this is. Well, here you've got a broad OH, so you've got an OH here, a broad absorption here at around about 3,000 to 3,500 is an OH. So anywhere around this region here is an OH. So it must be prop 2-ene-1-ol. It must be that one. And the other way, I suppose, of recognizing it is that in here you've got a carbon-to-carbon double bond, which is this one here at around about 1,600 to 1,700. So the compound is definitely prop 2-ene-1-ol because of this OH broad absorption here. The bond used to identify the compound, the OH or the alcohol, at 3,230 to 3,550. So that's taken directly from the data book. Remember to quote this. Or you could have had carbon-to-carbon double bond at 1,620 to 1,680, again from the data book, which is this one here. Wave number of range of bond used to identify the compound. Those are the numbers that you have to quote. Predict the relative boiling points of these three compounds from highest to lowest for 6 marks. Justify them. So first of all, you've got to get it right, and then you've got to justify it. So let's have a look what's in here. Have we got an oxygen bonded to a hydrogen, or a fluorine bonded to a hydrogen, or a nitrogen bonded to a hydrogen? Yes, we've got an oxygen bonded to a hydrogen here in prop 2-ene-1-ol. So that's going to have hydrogen bonding. Hydrogen bonding is the highest kind of is the strongest kind of intermolecular bonding, and so prop 2-ene-1-ol will have the highest boiling point. Next here you've got a polar bond here between the carbon and the oxygen, because oxygen is electronegative, so that's going to have a delta minus, the carbon's going to have a delta plus. So that's a polar bond. So between these molecules the intermolecular bonding will be dipole-dipole and propanol. So that's the next highest boiling point. So this is the highest boiling point, prop 2-ene-1-ol, next propanol, and then finally butane, which hasn't got any polar bonds, hasn't got any hydrogen bonds, it's just got weak van der Waals forces. So correct order: prop 2-ene-1-ol, higher boiling point than propanol, which has got a higher boiling point in turn than butane. Prop 2-ene-1-ol has hydrogen bonds, propanol has dipole-dipole forces, and butane has van der Waals forces. And then you've got to mention the strength of the intermolecular force in order are hydrogen bonds the strongest, followed by dipole-dipole, followed by van der Waals. So this question's about chlorine radicals, free radical substitution. Write 2 equations show how chlorine radicals react with the ozone molecules in the upper atmosphere. So the first equation is that Cl dot, which must have been made already, probably by Cl2 chlorine in the presence of ultraviolet light, an initiation step, making 2 Cl dots, and then there's a propagation step. So the Cl dot is then reacting with the ozone. Ozone's O3. The only thing it can turn into is O2. There's only 2 forms of oxygen, O3 and O2. So O3 must turn into O2. And then what have you got left? You've got a dot, you've got Cl, and you've got 1 of the O's left over to keep 3 O's on either side. The dot can go anywhere around this radical. Then this radical is going to react again. It's very reactive, a radical, and it's going to react again with more O3, and it's going to make 2 lots of O2 in a Cl dot. So it's going to react again, react with O3. The only thing that it can turn into is O2. 4 oxygens on the left hand side, so you can balance that by 2 O2s, and then you've got a Cl dot. And then this is a chain reaction in which it carries on and on and on and on and on, because the Cl dot is a catalyst, it's reformed. Chloropentafluoroethane is CFC. Draw its displayed formula. So what have you got? Chloro, Cl, penta is 5 fluoros. You've got 1 Cl and 5 Fs around ethane 2 carbons. So you can draw them any way you want. It's got to be displayed, so you've got to show the bonds. That must be done. It must be a displayed formula showing the bonds. 5 Fs and a Cl. They can go anywhere. 1,1,1 trichloroethane, CF3CH3 is one of the molecules being used as a refrigerant. Explain why 1,1,1 trifluoroethane does not lead to the depletion of ozone in the upper atmosphere. It's because it's got no Cl's in it. It doesn't contain chlorine. One of the steps in the synthesis of 1,1,1-trifluoroethane is the reaction of 1-difluoroethane CHF2 CH3 with fluorine in a free radical substitution reaction. Write two equations that represent the propagation steps in the conversion of this into this. Well, if you've got fluorine in a free radical, then you've got F2 in ultraviolet light making two F dots. So this time you're using F dots rather than Cl dots. But it's the same principle then. You've got turning CHF2CH3, CHF2CH3 and an F dot. It always makes HF, or if you're using Cl dot, it always makes HCl. It makes HF or HCl depending on whether you're using F dot or Cl dot. But that's always made, and therefore you can work out what's left. Well, I've got two carbons, and I've got two Fs, and I've lost one of the H's. Now, where does the H get lost from? That's the question. Does the H get lost from here, or does the H get lost from one of these three? So what's eventually going to happen is, where the H gets lost from, that's lost a bond. And if it's lost a bond, the bond is broken. And that bond is broken, and the electron, one of the electrons in the pair, has come back onto the carbon. So in other words, that carbon with the dot shows that it's missing a bond. That carbon has got two Fs, two bonds to an F, one to the C, so it's got two Fs and one to the C, and the dot represents the missing bond, the electron that was in that bond. So that's showing that that carbon is missing a bond, and an F's going to go onto there in a minute. So an F is going to join onto there and make CF not 2 but F3, and that's why I know that that dot is on that carbon, because that is going to be replaced, that H is going to get replaced by an F. So that H must be lost so it can get replaced by an F, and the dot is on that carbon there. What's going to happen next? This is going to react with fluorine then. So this reacts with F2. Okay, so this reacts with F2, always makes an F dot again because this is a catalyst in the chain reaction, and therefore we make CF3CH3 as it says in the question. A refrigerator contains 1.41 kilograms of this chemical. Calculate the number of molecules in the refrigerator. Give your answer to the appropriate number of significant figures. So why are we given mass? Why are we given mass? Why are we given a formula? We must be asked to work out the number of moles. So moles is this in grams. Moles is mass in grams divided by relative formula mass. So this in grams, a large unit number like a kilogram going into a smaller unit number like a gram. So you multiply by 1,000. So 1.41 multiplied by 1,000 is 1,410. You can work out with a periodic table that an F is a 19, the Cl is a 12 in terms of mass numbers, and H is a 1. And so if you add all of those together, the MR is 84. You've got 16.8 moles of this 1,1,1-trifluoroethane. Now, the number of moles multiplied by Avogadro's number gives you the number of particles. So number of moles, 16.8 multiplied by 6.022 times 10 to the power of 23 will tell you the number of molecules in that sample. To three significant figures. Why to three significant figures? Because some of the other values, like 1.41 kilograms, are to three significant figures. So three significant figures is needed because one of the other values is to three significant figures. There are growing concerns about 1,1,1-trifluoroethane as a refrigerant. Give one reason why the bonds in the molecules, such as carbon dioxide, absorb infrared radiation. Well, the reason that bonds absorb infrared radiation is that they stretch or bend. Vibrate, stretch or bend. Question number 6. Draw the skeletal formula. So you've got to draw the carbons in a line and not bother drawing the hydrogens at all. So you leave the hydrogens up from it. Draw the skeletal formula of propane. So that's 3 carbons, and you put them in a little kink shape, so in a little zigzag shape. 1,2-diol. So at carbon number 1 you've got an OH, and at carbon number 2 you've got an OH. So it's going to look like this. 1, 2, 3 carbons in a line, 1, 2, 3, and then an OH at carbon number 1, an OH at carbon number 2, and there's carbon number 3, and you've left off all the H's. You're not bothered drawing those in. That's the way that skeletal formula works. Write an equation for the oxidation of propane 1,2-diol under reflux, using O to represent the oxidizing agent. So propane 1,2-diol, so you can draw it now as a displayed formula with a C with two H's and no H, and a C with an H and no H, and a CH3 here now, an O to represent the oxidizing agent, and then it's going to form. Let's have a look what it forms. So this OH is a primary alcohol, so this is primary at the end because the C with the OH has got one other carbon attached to it, so the COH, one other carbon attached to it. This primary alcohol under reflux, so when you use an oxidizing agent, will first of all form an aldehyde group, a C double bond OH, and then that will oxidize again and form a carboxylic acid group. So you've got a carboxylic acid group here, a C double bond OH. Before that, it's turned from a primary alcohol into an aldehyde and then into a carboxylic acid group. This OH here, however, is a secondary alcohol group because the carbon with the OH has got two carbons joined to it, two carbons bonded either side, and a secondary alcohol turns into a ketone, in other words a C double bond O in the middle of a chain, and that can't turn into a carboxylic acid. It would need to be on the end to turn into carboxylic acid. It would need to be an aldehyde to turn into a carboxylic acid, so that stays as a C double bond O ketone group. Now let's have a look. 3 carbons is okay. How many H's? 1, 2, 3, 4, 5, 6, 7, 8, 9. 1, 2, 3, 4. So 1, 2, 3, 4, 5, 6, 7, 8, sorry, in this, 4 in this, and so we're going to need 2 H2O. It's going to form water. The O's remove the H's from here to make water, so we've got 4 H's, and therefore if we've got 2 in front of the H2O to make 4 H's to balance up with the 4 H's here to make the 8 here, therefore we're going to have 1, 2, 3, 4, 5 oxygens needed. We've got 2 here. We're going to need 3 other oxygens here. Draw a label diagram to show a setup apparatus for refluxing. So you've got a flask, it'll need to be labelled. Then you've got a condenser. The idea of reflux is that you heat it, and then any gases that go up here then get condensed and drop down into the flask. So they get returned back into the flask because they cool here. The hot gases cool, condense back into a liquid and return back into a flask. It's a way of heating this liquid, these reactants, without losing them as vapors. You also need no gaps here as well, so you can see how it's drawn with the condenser coming down, and maybe some kind of bung or something in here, but no gaps between the flask and the condenser, otherwise the gases would escape either side. Anti-bumping granules are placed in there. Why that? That's to prevent large bubbles from forming. Draw the structure of a different organic product formed when acidified potassium dichromate is not in excess. Well, not in excess, so the easiest one to show is that this would form an aldehyde group, and therefore it would stop at an aldehyde group if it's not in excess and would never form the carboxylic acid group. That's the easiest one to draw, where you've got a carboxylic acid group here, and this OH hasn't even turned into a ketone. So the carboxylic acid group hasn't formed, it's formed an aldehyde group here, and this one has stayed as an OH. You could say that one's turned into an aldehyde and this one's also turned into a ketone, but this one hasn't quite turned into a carboxylic acid group here. You could also say this one's turned into an aldehyde and a carboxylic acid group, but this one hasn't turned into a ketone group here, or you could keep this one as an OH and turn this into a ketone. So you can have any combination of aldehyde, carboxylic acid, or ketone, but not forming the full carboxylic acid and ketone groups. Question number 7 then. The alkene 3-methyl-pentuene, it's drawn for you here as the structural formula exists as E and Z isomers. Draw the structure of Z3-methyl-pentuene. So it looks like this. So pent is 1, 2, 3, 4, 5 in a line. 1, 2, 3, 4, 5 in a line, and it's got a methyl group at carbon number 3. 1, 2, 3. There's the methyl group. 1, 2, 3, and at carbon number 2 it's got an ene, pent-2-ene. So let's see if I've drawn the Z isomer or whether I've drawn the E isomer. So what do? We look to the left of the double bond, and then we find the atom with the highest atomic number. Hydrogen's got an atomic number of 1, carbon's got an atomic number of 6. So this group here would take priority because this carbon to the left of the double bond has got a hydrogen with an atomic number of 1, a carbon with an atomic number of 6, so this group takes priority. So remember that group. On the right hand side, let's see which group takes priority. We've got a carbon joined to the carbon of the carbon double bond, and we've got a carbon joined to the carbon of the double bond. So we've got 2 carbons joined here, each with an atomic number 6. So we carry on further down the chain. Joined to this carbon, we've got hydrogens with an atomic number of 1. Further down the chain here, we've got this carbon joined to hydrogens, but also joined to a carbon here with an atomic number of 6. So this group takes priority. So this group and this group are the 2 that takes priority. They're on the same side, both on the top of the double bond, so it is indeed Z. Name and outline a mechanism for the formation of 3-bromo-methyl-pentene from the reaction of this with hydrogen bromide. So you need to draw this and hydrogen bromide. What kind of mechanism is it going to be? Well, it's going to be electrophilic addition. We'll explain that in a minute. So now we've got the carbon-to-carbon double bond attacking the H of the HBr. The reason is that's slightly electronegative, so it's going to have a delta minus, that's going to have a delta plus. The electrons will attack the delta plus here. The H is going to bond onto one of these 2 carbons. We'll discuss which one it bonds onto in a minute. The Br breaks off and forms Br minus, and there'll be a pair of electrons from the double bond on the Br minus. Which one does the H bond to? Well, if it's the major product, and we're going to assume it's the major product, we'll check that out in a minute. If it's the major product, it goes onto the carbon that's got the most number of H's bonded to it. So this carbon has got 1 H bonded to it, CH. This carbon has got no H's bonded to it. It's got carbons bonded all along to it. So this H will go to this CH that's already got 1 H bonded to it, rather than this C which has got no H bonded to it. So it's going to form CH2. And then this carbon, because the double bond's broken, so there's a CH2 and a single bond here now, and this carbon now has only got 3 bonds, so it's short of an electron, it's short of a bonds and electron. It becomes plus. The Br minus attacks that plus with a lone pair of electrons, so the Br will join onto here. Let's see if we made the right choice by choosing the major product and the H joining onto this C rather than this C. So the Br, what is on carbon number 3? So we're going to end up with pentane with a methyl group at carbon number 3 and a Br at carbon number 3. We're going to have 3-bromo, 3-methyl pentane. 3-bromo, 3-methyl pentane. Yes, we made the right choice by choosing the major product and the H going onto this carbon rather than this carbon. Electrophilic addition, why? Because this is an electrophile, it's an electron pair acceptor, it accepts the electrons from the double bond. This is an electrophile, and I've got 2 reactants forming 1 product, so they're adding together. Explain why this is formed in the reaction, so why this is the major product rather than 2-bromo, 3-methyl pentane. It's because this C with a plus is called a carbocation, and if you count the number of carbons off that C plus, it's got 1, 2, 3. So it's called a tertiary carbocation because it's got 3 carbons bonded to the C plus. A tertiary carbocation is stable, more stable than the secondary carbocation, which would have a carbon with a C plus joined to 2 carbons either side of it, which is in turn a secondary is more stable than a primary carbocation that's got a C plus with just 1 other carbon joined to it. So this tertiary carbocation is more stable than a secondary carbocation. Had the H bonded to this carbon and the plus being here, then if the plus had been on this carbon, then the plus on this carbon would have been a secondary carbocation because this C plus would have had carbons either side. So your answer is that 3-bromo, 3-methyl pentane is formed from a tertiary carbocation, which is more stable than the alternative, which is a secondary carbocation, which would be the minor product. Question number 8. We've got some ethanoic acid reacting with some magnesium. An acid with a reactive metal like magnesium is going to make hydrogen, and we've got a graph showing the hydrogen being made. With the aid of calculations, showed that magnesium is in excess in this reaction. So let's have a look what data we're given about the magnesium. We're given 395 milligrams of magnesium, and we know magnesium, Mg, has got a mass number of 24. So we've got its Mr, 24, we've got 395 milligrams. We can convert that into grams. So if we go smaller into larger, we divide by 1,000, that's 0.395 grams of magnesium. Moles is mass in grams, 0.395, divided by the Mr, moles over Mr, over 24. So your first thing to do is 0.396, should be 395, 0.395 divided by 24.3, which is the accurate Mr of magnesium from the periodic table, equals 0.163. Now your next thing to note is you've got a volume. You've got 30 centimetre cubed of 0.6 mole dm to the minus 3 ethanoic acid. You've got a volume and a concentration. So concentration equals moles divided by volume. Concentration is moles divided by volume, so moles is concentration multiplied by volume. This volume, centimetre cubed, is going to be in decimetre cubed, so smaller into larger I'm dividing by 1,000, that's 0.03 decimetre cubed. So I'll multiply those two together and I end up with 0.018 moles of ethanoic acid. Now when you actually look in this equation, 2 moles of ethanoic acid only react with 1 mole of magnesium. So if I've got 0.018 moles of ethanoic acid, it will react, 2 moles react with 1, so it will react with half of that. So 0.018, 2 reacts with 1, 0.018 would react with 0.009, half of that. So I'm going to need 0.009 moles of magnesium to react with the ethanoic acid, and I've got 0.163. I've got more than I need. If I subtract these two numbers, it will actually tell me that I've got 0.0073 moles of magnesium in excess. What's my next thing here? So I've got 20 centimetre cubed of 0.8 moles decimetre cubed of ethanoic acid. I've got a new volume and concentration of ethanoic acid. Why on earth would they give me volume and concentration? Again, concentration is moles divided by volume, so moles is concentration multiplied by volume. The only reason they give me volume and concentration is if they wanted me to work out moles. 20 centimetre cubed, small units into a larger unit, a decimetre cubed that we need for this equation, divide by 1,000, so 0.02 multiplied by 0.8. is 0.016. I've got 0.016 moles of ethanoic acid this time. They must have wanted me to work that out, otherwise they wouldn't give me a volume and a concentration. So I've got 0.016 moles of ethanoic acid this time. Previously I had 0.018 moles, so I've got 0.016 rather than 0.018. So I've got slightly less, so I'm going to get less product. Let's have a look at my graph here. 0.018. 0.018 is the number of moles of ethanoic acid that I have. This time I've got 0.016. So proportionately, 0.018, if these went up in 0.02s, 0.02, 0.004, 0.06, 0.08, 0.01, 12, 14, 16, 0.018. So 0.016 would go up to this graduation here. So 0.018 goes up to here if I go up in 0.02s, and if I'm going up in 0.02s, 0.016 goes to here. So my graph will go to here, up to this line, and it's going to go more shallowly. The reason it's going to go more shallowly but through the origin is that it's going to go steeper because it's a higher concentration than before. It's 0.08, whereas before it was only 0.06. So it's going to go steeper because it's a higher concentration, so you've got more particles within the flask. You've got close particles are closer together, more successful collisions. So particles closer together in my newer higher concentration, it's going to go steeper, but only up to that line there, 0.016, because I've got less moles, because I've got less volume. Which of the following would form an orange-red precipitate when heated with failing solution? So I've got a nitrile as A, I've got carboxylic acid as B, which would turn sodium carbonate, make bubbles. I've got an aldehyde as C, which would make a silver mirror with warm toluenes, or would indeed form an orange-red precipitate when heated with failing solution. And then I've got a ketone as well. Answer is C, an aldehyde would form an orange-red precipitate when heating with failing solution. And as I say, the alternative test is warm toluenes reagent forming a silver mirror. Pentane nitrile made by the reaction of 1-bromobutane with potassium cyanide. So potassium cyanide makes a cyanide ion, a Cn- ion with a lone pair of electrons on the C, and the lone pair of electrons attacks the C of the CBr and releases the Br as a Br-. So the Cn- is a lone pair donor. It's a nucleophile, and it replaces the Br. It's nucleophilic substitution. It's D. Let's look at question 11 and 12. Propene can be made by the dehydration of propan-2-ol. So 1 mole of propan-2-ol should make 1 mole of propene. What I've been given, so I've been given 30 grams of propene MR42. So I've been given a mass and an MR. Moles is mass divided by MR. They want me to work out moles of propene. Similarly, they've given me grams and MR of propan-2-ol, mass and MR. They want me to work out the moles of propan-2-ol. So let's do that. Moles of propan-2-ol, 50 divided by 60, 0.833 moles. Moles propene, 30 divided by 42, 0.714. As I said previously, 1 mole of propan-2-ol should make 1 mole of propene. So 1 mole of propan-2-ol makes 1 mole of propene, so 0.833 moles of propan-2-ol should make 0.833 moles of propene. However, when we work it out, there's only 0.714 moles of propene. So the percentage yield is how much we did make, 0.714, divided by how much we should have made, 0.833 moles, multiplied by 100%, 85.7. So the answer is closest to 86%. The answer is D. Sulfur dioxide. So sulfur is in group 6, so is oxygen. So they're both non-metals on the right-hand side of the periodic table, formed when fossil fuels are burned. Which of the following statements is true? Let's try and rule out what's not true. Sulfur dioxide is insoluble in water. No, we know sulfur dioxide is responsible for acid rain. It dissolves in rainwater and forms something called sulfurous acid, which reacts with oxygen out the air and forms sulfuric acid and kills fish and plants. So no, it's not insoluble in water. It's very much soluble in water. Sulfur dioxide is basic alkaline oxide. Now you get an alkaline or a basic oxide when you get a metal reacting with oxygen, like magnesium oxide or sodium oxide or potassium oxide. Sulfur dioxide is acid. It's an acid oxide. We know that because it's acid rain, and sulfur is a non-metal. So a non-metal oxide like sulfur dioxide is an acid oxide. Sulfur dioxide is ionic. No, it's not ionic, because sulfur dioxide, two non-metals coming together form molecular compounds with van der Waals forces between them, or at best dipole-dipole attractions between them. They don't have ionic properties. That happens when a metal that wants to lose electrons from group 1 or group 2 or group 3 reacts with something from group 6 or 7 that wants to gain electrons, and they transfer electrons between themselves and form ions that strongly attract together. No, it's not an ionic compound, so it must be this one. Sulfur dioxide can be removed from waste gas in a power station in an acid-base reaction with calcium oxide. Now that's true. You need to either learn that or understand the other chemistry to work out why those B, C and D can be can be decided not to be the right answer, to leave A as the correct answer. Let's look at question 13. I'm going to do spoilers on this one, so I'm going to tell you the answer is B. But the reason for it to be B is, let's have a look at C first of all. The OH minus going to take the H, but then this HC should go between the two carbons to form but2ene. So in this case you're getting some kind of strange mechanism here where it's going on to the C, and I don't know why that would be. The bond from the C to the H goes between the two carbons, not onto the carbon. That's a strange mechanism. D is some kind of elimination reaction here, so it's some kind of nucleophilic substitution reaction rather, where the OH is bonding to the C and the Br is being released, so you'd end up with a secondary alcohol here with the OH on here and the Br being released. So that's acting as a nucleophile and nucleophilic substitution reaction, but it's not going to form a carbon-to-carbon double bond, so C and D are incorrect. Let's have a look at A and B then. Going for an H, so the OH minus attacking an H, the electrons from the H going between the C and the Br being released. That looks very promising. And the OH minus reacting with the H, the bond going between the two C's and the Br being released. And that's a perfectly good mechanism as well. The only difference is that this one's going to form a double bond here between the carbon number 1 and carbon number 2. So you're going to end up with 2-methyl but3ene, whereas this one you'll end up with 2-methyl but2ene, because the double bond will be here at carbon number 1, 2. So this one's correct. So let's just have a look again. The OH minus removing the H to form water. The bond here going to form a double bond in the middle here between these two carbons, and the Br being released as Br minus. And carbon number 1, 2-methyl but2ene. So that's your correct answer, is B. Question 14. An organic compound is found to contain 40% carbon, 6.7% hydrogen and 53.3% oxygen. So if we had 100 grams of it, let's say, we'd have 40 grams of carbon, 6.7 grams of hydrogen and 53.3 grams of oxygen. If you divide by the mass of each of them, so carbon's 12, hydrogen's 1 and oxygen's 16, you'll find out the respective ratio of the amounts of each of those in there. So if I take 40 divided by 12, 3.3, 6.7 divided by 1, 6.7, 53.3 divided by 16, so these are the amounts divided by the relative atomic mass of each of them. Then I've got a ratio of 3.3 to 6.7 to 3.3. If I divide by the smallest, which is 3.3, I get a ratio of 1 to 2 to 1. Now, what's 1 to 2 to 1? Ethanol, well, it's got 2 carbons in it. That's got 2 carbons. Methanol is CH3OH. So that's not CH3OH or CH4O. CH4O, C1H2O doesn't match methanol. Methanoic acid is CH double bond OOH, so that's got 1 carbon, 2 H's and 2 O's, 1 carbon, 2 H's, 1 O, so it doesn't match either of those, so it's got to be ethanol or ethanoic acid. So if I double these amounts to end up with 2 carbons, 4 hydrogens, 2 oxygens, that's 2 carbons, 4 hydrogens, 2 oxygens, that matches ethanoic acid, 2 carbons, 4 hydrogens, 2 oxygens. The repeating unit of the polymer is this. What would it form from? Which of the following molecules would form a polymer containing this repeating unit? So what you do is, before it's actually bonded either side, this has been a monomer. So those 2 carbons have had a double bond that's broken and then formed a single bond either side. So if we imagine this and remove those 2 bonds either side and put a double bond between it, what it's been is, it's been 3 carbons in a line, with a double bond here, at carbon number 1 and a methyl at carbon number 2. So it's been prop-1-ene, 2-methyl-prop-1-ene, 2-methyl-prop-1-ene or methylpropene. Let's have a look at questions 16 and 17. Which of the following statements is true? Position A represents the mean energy. Now, position A represents the energy that most molecules have coming down from the peak of the curve. The mean energy is slightly to the right of the peak. Addition of a catalyst moves the activation energy to the right. Now, it lowers the activation energy, so it moves it to the left. The area underneath the curve to the right of the activation energy represents the number of molecules with enough energy to react. Yes, underneath the curve represents the number of molecules, and those to the right of the activation energy have got the sufficient energy to react, so C is correct. The position of the peak, let's just check D. The position of the peak of the curve at the higher temperature is further away from both axes. The position of the peak at a higher temperature now actually lowers itself, so it would come down something like that to keep the area underneath the curve the same in both cases. It would lower and then shift towards the right. So D is incorrect. 17. Tridecane C14H30 is found in crude oil, decomposes to form one molecule of hexane and 3 more molecules. Which is correct? Well, let's have a look. Let's try and eliminate some. So B forms hexane, that's right, C6H14, but it forms 2 other molecules. So B is incorrect because it's only forming 2 other molecules, and it says it needs to form 3 other molecules. C, what's wrong with this? Well, it's actually not forming hexane, it's forming C5H12, which looks as if it's propane, so it's not forming hexane at all. So C is incorrect. D doesn't look as if it balances. If I check the number of hydrogens, I've got 30 hydrogens here, I've got 14, add 6 is 20, and 2 16s is 12, that's got 32 hydrogens. It actually doesn't balance, so A is the only one that's correct. Let's just check. C14H30, C6 and 4 is 10, and 2 2s are 4, it makes 14 carbons on the right, 30 hydrogens on the left, 14, add 6 is, add 10 is 24, add 8, let's check that out, hold on, 14, add 8 is 22, add 8 is 30, yes, it's got 30 hydrogens on each side. Does it form hexane? Yes, C6H14 is hexane, 3 other molecules, 1 there, and 2 lots of ethene, yes, it's definitely A. Question 18 then, which of the following is the general form of cyclic alkenes such as cyclohexene? So let's have a look at cyclohexene. So cyclohexene has got 6 carbons in a ring, and then on each of the, well, on 4 of the carbons it's got 2 hydrogens, and on the other 2 carbons it's got 1 hydrogen. So it's got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So it's C6H10. So if I double the number of carbons, C6 to 12, I'd have to take away 2 from the 12 to make 10. So your answer is C6H10, 6 times 2 is 12, take away 2, CnH2n minus 2. CnH2n minus 2, it's answer B, because it's C6H10. If I double the 6, that makes 12, take away 2 to make the 10. A and B react together in this reversible reaction. I'm actually going to do spoilers on this one. We actually have a look at the start, then I've got 10 molecules of A and I've got 10 molecules of B. I've not got any in C of C and D yet. I've got none of them because the reaction hasn't started. Then at equilibrium, I don't know how much A I've got. Does it tell me how much B I've got? Yes, I've got 4 molecules of B, it tells me that, but I don't know how much of each of these I've got. So at equilibrium, the amount of B has gone down from 10 to 4. I've used up 6 moles of B, because it started at 10 and has gone down to 4. If I've used up 6 moles of B, where's it gone? So 6 moles of B have gone. Let's have a look then. 1 mole of A reacts with 3 moles of B. So 2 moles of A would react with 6 moles of B. So I've got 1 to 3 ratio, 6 moles of B have been used up, so 2 moles of A must be used up. The same amount of C is made as A, so if 2 moles of A are used up, then it makes the same number of moles of C, because 1A makes 1 mole of C, so 2 moles of A would make 2 moles of C. And when 1 mole of C is made, 2 moles of D are made, so 2 moles of C would make 4 of D. So let's add it all up and see what I've got. So 10 moles of A to start off with, I've used up 2, I've got 8 left over. I've got, at equilibrium, I've got 4 moles of B remaining, it tells me that in the question. C, I start off with nothing, made 2, so I've got 2. D, start off with nothing, made 4, so I've got 4. So the total is 8 plus 4 is 12, add 2 is 14, add 4 is 18. So my answer is C, 18. That 16 is wrong. It should be C, 18. Let's have a look at question 20 first of all then. Which of the following is the mass of hydrated copper sulfate? And it tells you hydrated copper sulfate CuSO4 5 lots of water, Mr249.6, required to make 50 centimeters cubed of 0.4 mole dm to the minus 3 solution. So I've been given a volume 50 centimeters cubed and I've been given a concentration 0.4. I can work out the number of moles because concentration is moles divided by volume, so moles is concentration multiplied by volume. The volume needs to be in decimeter cubed, so 50 centimeters cubed, centimeter cubed going into decimeter cubed, a smaller unit going into a larger unit is divided by 1000, so that's 0.05. So let's do spoilers. Moles is concentration times volume. Moles is 0.4, that's the concentration, multiplied by 0.05. That's 50 centimeters cubed, divided by 1000 is 0.05. I've got 0.02 moles of copper sulfate in my solution. So what's the mass of copper sulfate that I needed to add? So to get 0.02 moles in there, moles is mass divided by mR. If moles is mass divided by mR, then what I've been given the mR, I've got the number of moles in there, I've worked that out previously as 0.2, so I've got moles, I've got mR, mass equals moles times mR, 0.02 is my number of moles, mR 249.6, 4.99 grams, the answer is D. Let's have a look at question 21 and 22, not very nice questions here really. 21. Which of the following changes, so increase in pressure adding the catalyst, increase in temperature and removing the carbon dioxide, does it affect the equilibrium yield of hydrogen? What the equilibrium yield of hydrogen means, shift the position of equilibrium to the right to make more hydrogen. So effect on equilibrium of hydrogen, increase in the equilibrium yield of hydrogen would mean shifting it to the right to make more. Decrease in the equilibrium yield of hydrogen would mean shifting it to the left to make more. Effective value on equilibrium constant. Now that's interesting because the only thing that affects the value of the equilibrium constant is temperature. So increased temperature would increase the effect, would increase Kc, but decreasing Kc, the only way that we're going to affect Kc, either to decrease it or increase it, is to change temperature. That's the only thing that affects Kc. So Kc can't be decreased, changed by increasing pressure. A is definitely wrong. And also removing CO formed, increase in Kc, no, that can't be right as well. So A and D are definitely wrong, because if we're going to change Kc, decrease it or increase it, as is the case in AC, we'd have to change the temperature, and it doesn't mention changing the temperature. So either B or C are correct. Increasing the temperature, increase on Kc, very possibly increasing the temperature could increase the Kc. This one, no effect on Kc, so maybe the catalyst could do that, have no effect on the Kc. There's only temperature that would change Kc, so no effect is plausible. So it's either B or C. Let's have a look. Adding the catalyst increases the yield of H2. Now, adding a catalyst doesn't shift the position of equilibrium to the right or the left. Adding a catalyst just speeds up the forward and backward reaction, so the equilibrium is achieved more quickly. So that's clearly wrong as well. It's not going to affect the position of equilibrium. So the answer is most definitely C. Let's just check out then. Increase in temperature changes, increase the value of Kc, very possibly. Increase in the temperature increases the effect, increases the yield of H2, in other words, makes more H2, shifts the equilibrium to the right. Let's check that. Increase in temperature, by Le Chatelier's principle, that it would try and lower the temperature of the system, of the surroundings. So would it shift to the right? Increase in temperature, Le Chatelier's principle say it will try and lower the temperature to oppose that change, and going to the right is endothermic, does take in heat. Yes, so more H2 would be produced. So taking in heat to lower the increased temperature and to oppose the change. C is the correct answer. Enthalpy value given in table 3. So this refers back to this reaction again. So the enthalpy change, let me just do spoilers, enthalpy change, bond enthalpy equals, or enthalpy change 206 equals bond enthalpy of the reactants take away bond enthalpy of the products. That's what BERP stands for. Bond enthalpy of the reactants take away bond enthalpy of the products. So 206, which is my enthalpy change, equals the bond enthalpy of the reactants. Now what's in the reactants? CH4. So what's the bond enthalpy of those CH4? 4 carbon to hydrogen bonds. Well, a carbon to hydrogen bonds is 413, and there's 4 of them, so 4 times 413 to represent those 4 bonds in CH4. An OH bond is a 463. In H2O there's an O to an H and no to an H, so there's 2 OH bonds, so that's why I've got 2 times 463 for this enthalpy change. Now the products, take away the bond enthalpy of the products, so I've got to take away carbon monoxide, a carbon to oxygen double bond. It doesn't tell me that, so I'll just have to leave that as minus the carbon monoxide bond here. Is that what it wants me to find out? It does. It wants me to find this value out. Take away 3 lots of H2. So a H to H, a H2 is a 436. So I'm taking away 3 lots of 436. Take away 436. If I rearrange that equation, I'll end up with 206 equals 1652. That's this, the product of these here, plus 926, which is this one, minus the bond enthalpy change of bond enthalpy of carbon monoxide, which I don't know, minus 3 times 436 is minus 1308. I'll take these 206, actually I'll take the minus carbon monoxide to this side, so it ends up as a plus. So the minus CO bond enthalpy will come over here and end up as a plus. 1652 plus 926 minus 308, and my 206 comes over this side and ends up as a minus, so it's 1064. So your answer is B. Tricky question this, so I'm going to do spoilers to show you how it's done. So 2 moles of an ideal gas. So I've got, what have I got? I've got pressure times volume equals nRT. So increase in pressure. Which one's going to increase pressure? Well, I'm going to eliminate things that aren't going to change, because I don't have to work out the exact value of pressure. I just need to work out when things are changed, how much the pressure's gone up by as a factor. So is it doubled, tripled, quadrupled, whatever. So I just need to work out how much it's gone up by, and I can eliminate from some of these calculations the things that aren't going to change, so I can work out how much it's gone up by rather than its precise amount. So volume isn't going to change, V is not going to change, it's a fixed volume. N, the number of moles, is 2, so that's not changing. R is the gas constant, that's not changing, so V, N and R are not changing. So P equals, P, V isn't changing, R isn't changing, N is 2, so P equals N times 2, and the V and the R are just constants in there, so I'm going to leave those out for the time being. because it won't really matter. Those are just numbers that I'm going to include in every calculation. So when I'm working out how much it's gone up by, those are irrelevant. So let's have a look for A, increasing the temperature from 20 to 200. So my pressure is 2 times 293 is 20 degrees C. 273 add 20, so turn it into Kelvin. Remember, temperature's got to be in Kelvin in this equation. 2 times 293 is 586, and the new pressure is pressure 2 moles 2 multiplied by 473, because 200 is 273, add 200 is 473, 946, so it's gone up from 586 to 946. It's nearly doubled. The way that I'd work out how much it's going up by a factor of 946 divided by 586. If I divide the bigger by the smaller, I work out how much it's gone up by. It's multiplied up by a factor of 1.61 times bigger. Let's have a look at B then. Adding another mole of gas to the flask. So pressure equals 2 moles times temperature has gone up to 3 moles times temperature, because the number of moles has gone up by from 2 to 3. So it's gone up by a factor of 2 up to 3. So it goes up by a factor of 3 divided by 2. It's gone up by 1.5 times. 1.5, 2t comes out as 3t. So it's gone up by 1.5 times. C, adding half a mole of argon gas. So the number of moles in the first instance is 2, and then it's gone up to 2.5 because I've added half a mole of gas when I've made the change, and increasing the temperature from 20 degrees C, which is 293, so 2 times 293 is 586, up to 150, so 273 add 150 is 423, multiplied by 2.5, because I've got 2 moles of gas and another half, 2.5, it's gone up to 1057.5. So this one has gone up from a pressure of 586 to 1057.5. It's gone up by a factor of 1057.5 divided by 586. It's gone up 1.8 times. And then finally D, removing half a mole of gas, so it's gone from 2 moles down to 1.5 moles here now, from 20 degrees C, that's 273, add 20, that should be 293 there instead of 283. 2 multiplied by 293 is 566. 1.5 multiplied by 573, so that's 273, add 300 is 573, gone up to 859.5. So it's gone up by a factor of 1.5 times. 859.5 divided by 566, 1.5 times. So which one has gone up the greatest number of times? 1.61, 1.5, 1.8 and 1.5. The answer is C, because it's gone up 1.8 times from its original amount. A tricky question.